Welcome Math 212 students. We are looking at Chapter 8 today, 8.1 specifically, and we are going to talk about geometry. So for your Common Core standards, you're going to start with geometry in kindergarten, where you're going to be looking at different shapes, 2- and 3-dimensional shapes. You're going to continue on in 4th grade, looking at angles and lines. In 5th grade, you're going to start plotting points on your Cartesian coordinate system. 6th through 8th grade, you're going to continue on with area and volume and transformations, and finally get into Pythagorean theorem and even the distance formula. So in this particular section, we are going to look at these topics. A few different examples of why we need geometry and how we've used geometry, talking about the boundaries of our land, doing surveying, looking at maps, building houses. All of these different things have been influenced by geometry. One of my favorite games is Tetris, watching those little shapes fall down and flipping those shapes around so that it will fit where I want it to. Flipping those shapes around, that's called our transformations. We can flip them left, right, spin them around, make them upside down. Another type of game that we can look at, Rubik's Cube, Minecraft. We used to play as kids a game called Battleship, where you would try to guess where somebody had hid their different battleships, basically. Looking at our different shapes in how we've created things, our nuts that are hexagonal so that we can grab them with a crescent wrench, and a fire hydrant plug that's pentagonal. We already said that. Alright, in art, this is pretty interesting. If you look at those two lines, and if I were to ask you which line is longer, your eyes are going to lie to you because of the way these two lines are drawn. Now, if I asked you the exact same question here, you would say they're of equal length. But going back here, because you see this line AC is cut in half, you see it is shorter. Very interesting things that our eyes will do to us. So, and this is just explaining that fact, and talking about it leads us into what we call spatial sense and how that's developed in our young children. And we are wanting to develop this spatial sense in our kids. So we have different ways to do that. We can have students copy shapes. We can have them play with 3-dimensional shapes. We can have them draw. In this one, we have two triangles that are exactly the same. We would call them congruent, but one is just flipped around. Most students can see that this first triangle is isosceles, because you can see that the two sides here and here are of the same length, but they don't see it when they're looking at this triangle, even though both of these two sides here are of the same length and this one is isosceles. Additionally, they'll look at this triangle and they'll say that he's obtuse, but they won't necessarily notice that he is obtuse in addition to being isosceles. And this just goes, just says all of that stuff in the words, but not with the pictures, so that you can look at. Your visual memory and being able to draw something, there are different mind games that you can play, such as those different games where they'll show you a path and then you have to remember that path, and it does increase your cognitive abilities and your spatial thinking in order to memorize and develop this visual memory that you have. In this side, they're going to talk to you about the fact that people decided just because we could look at something and kind of say it's true, that wasn't sufficient for us. We wanted to know exactly why it was true and to prove that it was true. So we started looking at things such as the Pythagorean theorem was developed, and why your sides outside of a square, they're all the same length, but the diagonals are not the same length. But the two diagonals in this square are exactly the same length to each other, and how this a squared plus b squared equals c squared developed. So we wanted to carry on with this, and we wanted to figure out why this is happening. We wanted to prove that it was happening. So Euclid, about 300 BC, he wrote The Elements. It is a book that we still study in mathematics and advanced geometry today. Even still, he realized in this that you can't define everything and you can't prove everything. There are some terms that you have to simply say, this is what I've defined it to be. There's nothing really to prove, such as what a point or a line or a plane is. I've said that this is what it is, and there's really no way to prove that it is. It is those things. Or trying to figure out how to describe a circle or round and what that means. So these are Euclid's 5 postulates. And he says you can draw a straight line from any point to another. Okay. You can produce a finite straight line continuously in a straight line. Okay, that sort of makes sense. And to describe a circle with any center and a distance. So you've got a center, and then you've got a distance from that center. So that would look something like, let's see if we get, if I start drawing, let's get my pen here. So I have a center, and then doesn't matter what my distance is, but all of the distances from that would be the same. All right angles are equal to each other, meaning that if it's a 90-degree angle, then it's a 90-degree angle, and 90-degree angles are equal to each other. Now, this last one doesn't really make a whole lot of sense if you're trying to figure out what in the world it means. However, there was an Englishman that made a lot of sense of it, and what he says is if you're given a line, so a straight line continues on and on forever, and you've got a point and it's not on that line. So here's a point, it's not on that line. It's possible to draw exactly, and exactly means no more, no less, means can't draw two. So I can draw a line through this point and it be parallel, and it be parallel to that. I'll make the point a little bigger, and it actually went through there. So, and there's only one way to do that. So that's what that last postulate meant, and John Playfair really did a great job of kind of putting that in layman's terms so that we can all understand what was meant by that. Here are definitions. Point has no dimension, so it's just a dot. That's it. And you can't describe it as having any width or length. A line goes on and on forever in both directions, and I'm going to put arrows on either end because it continues on and on in both directions and doesn't stop. A line is a bunch of points, and so this line here is a bunch of points, like machine gun fire, all really close to each other, and then there's points in between those points and points in between those points. So that's what it means to be an infinite collection of points. A plane is this flat surface like a floor or a countertop, and it extends in all directions as well. Alright, so let's just look at this. Draw a point on a piece of paper. How many different lines can we have to go through that point? So there's a point, and I can have a line that goes right through here. Oops, let me make my point. Right here. It can go there, it can go there, it can go. So we can say that we can draw an infinite number of lines that go through that one point. Draw 2 points on a piece of paper. How many lines can you go through? Just one. Just one. So we say in geometry that 2 points define a line. 3 points on a piece of paper. How many lines can you draw to go through all 3 points? Well, depends on how I draw my points. If I draw them like this, none. If I don't do that one and I consider this one, I can do one, but they have to be what we call collinear. So that's why they said it depends on that one. Talking about line segments and rays. A line segment is just portion of a line that's kind of chopped off. So if I had this line, chink, chink, and let's put 2 points on it, say, call them A, B. AB would just be this chunk right here, so, and I would write that as AB with a line segment over the top. A ray would be, using mine from above, I could say the ray AB, and that would be this guy right here. I could, let's do a different color here. Ink color. Oops, ink color. Let's do purple. And let's say I wanted to go this way. Oh, silly thing. Oh, there you go. Okay, so I could go this way, and that would be ray BA. Now ray BA and AB are not the same thing. One goes to the left and one goes to the right. Be sure and note that. This is nice little table showing you what we just looked at. Lines, possible ways two lines may be related. They can intersect. Okay, and this is their intersection point here. Yeah. Perpendicular lines just means that they intersect at a right angle, 90 degrees. Concurrent lines just means that we have several lines going through the same point. Parallel lines means that I have lines and they do not, and they don't intersect, and they're in the same plane. Now that's kind of a, let's look at what it looks like when they're not in the same plane. This is a skew line when they're not parallel, and that would mean, and they don't intersect, but they're, I like this little shed here. Went and got this little shed for you because you could see that they don't intersect. You got to visualize this three-dimensionally. They don't intersect, like CD here, and let's say BF. They don't intersect, but they're not in the same plane. So they are skew lines. Next we're going to look at angles. Vertex is the little end point where they meet there, and then we have our two sides, and this would be the angles measure. You can see the interior and the exterior of the angle. Pictures are worth everything to me. I like the pictures. So if we're going to name these angles, I could call this angle A. This right here would be angle 1. This guy right here would be angle 2. Of course, and you've got it from there. There are different ways that we can name our angles. If you'll notice, angle 2, there he is right here. I could call angle 2 angle KML or angle LMK. I can't just call him angle M because angle M would be this great big angle possibly. And you see, so I really have to be sure, you know, because M could be like this great big angle, or it could be one of these two little angles. I don't know. So we have to make sure that we're very clear. Mathematics is really clear. So if I look at that one, that's angle 1. Angle 1 could be angle JMK or angle KMJ. We measure our angles with a protractor, and we measure our angles in degrees. So here's a couple of protractors. You'll notice they're usually clear. You'll have a little, you don't really put your line on this bottom piece right here. You put it right there. You put your line so that you can see through it, and you put it right there. You'll have one of your rays going this way. You be sure you put the one side at the 0, and then you'll measure it this way. This one looks like he's, I don't know if that's 70, then he looks like he's about, would be about 65. What do you think? He's like 63, 63 and a half, something like that. That's how I would describe it. Be sure you put your degree measure on there. This angle, notice that the vertex is right here on the middle portion, and I'm going to measure this way, and that'd be like 126 or so, somewhere around in there. Oops, my little degree got a little big. Sorry about that. I'll put a little circle there. Okay, and here they are telling me those are about what my measure. I could have said 64, I could have said 125. You know, it looked a little over than that, but could have said 127. I've still been right, because part of that is a guess. Now, when you've got a really accurate protractor and it's got a really bunch of little bitty tick marks, then you can measure things in minutes and seconds. Ours, there's no way we could measure in minutes and seconds. We could barely get to the units of degree there. From here over to here is 180 degrees. If you go all the way around, that is 360 degrees. Just think about it. If you're driving your car and you do a 180, that means you are going the other direction. If you do a 360, you have spun entirely around. A right angle is this 90-degree angle. That's how we've defined it. So that is a right angle. We specify a right angle using a little bitty, see, you can't really tell that mine's a right angle, but once I put that little bitty square in there, you know I've drawn a right angle. If I draw an angle that's bigger than 90 degrees, I'm going to call him obtuse. And if I draw an angle that is less than 90 degrees, I call him a little cutie angle. So let's look at a couple of angles here. They've given us a right angle, he's 90, here's a little cutie, an obtuse. A straight angle just means that it's 180 degrees. Reflex angle just means it goes all the way. I don't think they even defined reflex, but there you go. Adjacent to just means that we have the same vertex, and those two angles are side by side. Now, in that, they must share a side for them to be adjacent. Their interiors are disjoint, meaning that all the points that are in here are different than all the points that are in here. So let's look at an angle here. So I've got an angle here, and I've got an angle here. So let's look at DAB, angle DAB, and angle PAM. They are not adjacent because they do not share a common side. If I looked at angle DAM and PAB, they are not adjacent because the interior of PA, I wrote PAB, I meant to write PAM, I don't know what was, I said it but I didn't write it, you know how that goes. If I look at the interior of PAM and I look at the interior of DA, and I wrote a B here, what is wrong with you? Okay, and I look at the interior of DAM, I see that they share common interior points, so they are not adjacent. Always helps to look at those. Complementary means they add up to 90. So this angle and this angle are complementary. If I look at, so I would write it like this, DAP, and I'm making sure I do the right ones here, PAM, are complementary because they add up to 90 degrees. I could say the angle PAM and angle PAB, so that would be this guy and this guy are supplementary. So these are complementary and these are supplementary because they add up to 180. Looking at vertical angles, so where did my pen go? There he is. Angle 1 and 7 are equal to each other. If you have two lines and they intersect, the vertical angles are equal to each other, and they kind of look like it too. Look at 3 and 5 and you can see how they equal each other because they are vertical angles. Angle 4 and 6 also equal each other because they are vertical angles as well. In getting the notation on this right, we say that they are angle 1 and angle 7 are congruent because their measures are equal. Or I could say that the measure of angle 1 equals the measure of angle 7 because this actually refers to the numbers. We don't like to use an equal to sign unless we're talking about numbers. Although if we're talking about numbers, use the equal to sign, but if we're just talking about that they're the same, then you'll use this congruent symbol, and that's how you would use that. So here's a proof showing that vertical angles are congruent. So you would look at this and you say measure of angle 1, measure of angle 2 are supplementary, they form a straight angle. I would say that the measure of angle 2 and angle 7, so these two are also a straight angle because they form a straight angle. Then I could say that the measure of angle 1 equals the measure of angle plus the measure of angle 2 equals measure of angle 7 and 2 because they're both equal to 180. And then using our algebra, subtracting that from both sides, I can say that measure of angle 1 equals the measure of angle 7. And that concludes our lesson for 8.1. And you guys have a good day. Thank y'all.